Bismillah ar-Rahman ar-Rahim. Matrix A is of size m by n. The rank of A is R, which is less than or equal to the minimum of m and n. The nuclear norm of matrix A is the sum of its singular values. If the singular values of A are sigma 1, sigma 2, all the way to sigma r in non-ascending order, if these are the positive singular values of A, then the nuclear norm of matrix A is the sum of those singular values. We want to verify that the nuclear norm is subadditive, it obeys the triangle inequality, and that it is submultiplicative. Let's first show that it is subadditive. And for this purpose, we will write down another definition for the nuclear norm of A. So the claim is that the nuclear norm of A is also this quantity, psi, which is the maximum of the magnitude of the trace of Q Hermitian times A. Q is a matrix of the same size as A, so it is a matrix of size m by n. And its maximum singular value, its induced L2 norm, its spectral norm, is less than or equal to 1. The claim is that this psi is exactly the nuclear norm. To prove this, psi, because it's the maximum of this quantity, psi is greater than or equal to this magnitude of the trace of Q Hermitian A if we make a specific choice of Q. And our specific choice of Q will depend on the SVD of matrix A. So suppose that A is equal to U S V Hermitian. And here I will do the reduced SVD. So matrix A, which is m by n, it is U, which is a matrix with orthonormal columns of size m by r. S is a diagonal matrix of size r by r. It has those sigmas on the main diagonal. And then V Hermitian is of size r by n. The columns of matrix V are orthonormal. So what we will do is that we will take Q to be equal to U and V Hermitian, U and V Hermitian, and between them we will put identity r by r. So our choice for matrix Q, it's a matrix with the same reduced SVD as matrix A, but now the diagonal matrix of singular values is replaced by identity. So matrix psi has r strictly positive singular values, all of them are equal to 1. This Q is feasible for our optimization problem, because in our optimization problem we have the constraint that the maximum singular value of matrix Q is less than or equal to 1. Here we choose the maximum singular value to be 1. In fact, we choose all the positive singular values to be unity. So rather than solving the maximization problem, we fix Q, but of course we need to fix a feasible Q. And then psi, because it's the maximum, is greater than or equal to the magnitude of trace Q Hermitian A. Now write down Q and A using their reduced SVD. So this is the trace of Q Hermitian. It will be V times U Hermitian, and A is U S V Hermitian. This is the magnitude of the trace of, let's see what we have here. Matrix U has orthonormal columns, so U Hermitian U is equal to identity. This is identity of size r by r. Now we have V, S, and V Hermitian. The claim is that this is equal to V Hermitian V, S. We are using here the property of the trace that if we have two matrices, phi and omega, phi is m by n, omega is n by m, then the trace of phi omega is equal to the trace of omega phi. So here in our problem, we have V, S, V Hermitian. V times S, that's a matrix of size n by r. V Hermitian is a matrix of size r by n. So the trace of this product is the same as the trace of V Hermitian, Vs. Now, V is also a matrix with orthonormal columns. So V Hermitian V is identity of size r by r. So this is the magnitude of trace S. And the trace is the sum of the singular values, and they are positive. So this is just the sum of the singular values of matrix A. And this is the definition of the nuclear norm. So our quantity psi is greater than or equal to the nuclear norm, defined as the sum of the singular values of matrix A. To prove that psi is the nuclear norm, then we need to prove an inequality in the other direction. We need to prove that psi is less than or equal to the sum of the singular values. The magnitude of trace of Q Hermitian A by the Neumann trace inequality is less than or equal to the sum j from 1 to r of sigma j of A, sigma j of Q, the product of the singular values, and each sequence of singular values is arranged in a non-ascending order. Now, we have a constraint that we want matrix Q to have a maximum singular value that is less than or equal to 1. So we can upper bound this by 1, and this sum here is less than or equal to summation j from 1 to r, sigma j of A. And this is the nuclear norm. Now, on both sides, take the maximum over matrices Q. So the maximum of magnitude trace of Q Hermitian A over matrices Q of size m by n, such that the spectral norm of Q is less than or equal to 1. This is less than or equal to the sum of the singular values. So psi is less than or equal to the nuclear norm of A. So the nuclear norm of A can be written as the sum of the singular values, or it can be written as the result of solving this constraint optimization problem, maximizing the magnitude of the trace of Q Hermitian A, where Q is of the same size as A, and the L2 norm of matrix Q is less than or equal to 1. That is, the maximum singular value of Q is less than or equal to 1. Now, using this result here, we can prove that the nuclear norm is indeed subadditive. So let's take another matrix B that is of size m by n. The nuclear norm of A plus B, if we use this definition here, is the maximum Q of size m by n, L2 norm of Q less than or equal to 1, the trace of Q Hermitian, and then here I put A plus B. Now, this is Q Hermitian A plus Q Hermitian B, and the trace of the sum of these two matrices is the sum of traces. So this is equal to the maximum, and then we have the magnitude of trace Q Hermitian A plus the magnitude of trace Q Hermitian B. Now, the maximum of the sum is less than or equal to the sum of the maximum. So this is less than or equal to the maximum Q in C m by n, L2 norm of Q less than or equal to 1 of the trace of Q Hermitian A plus maximum Q of size m by n, L2 norm of Q less than or equal to 1 of the magnitude of trace of Q Hermitian B. This is the nuclear norm of matrix A, and this is the nuclear norm of matrix B. Okay. The idea that the maximum of the sum is less than the sum of the maximum is intuitive. Here, we are maximizing over each term on its own. So here I'm trying to find the Q matrix that maximizes this and the Q matrix that maximizes this. This Q matrix here that will maximize this quantity will be in terms of the SVD of matrix A, the U and V matrices of matrix A. But here it will be the U and V matrices of matrix B, as we did above. But here we want a single matrix Q that maximizes this summation here. So definitely we can get a higher value by maximizing this term on its own and maximizing this term on its own. To be formal, we have f of alpha plus g of alpha. The supremum of this summation, alpha is in some set S, is always less than or equal to the supremum of f of alpha plus the supremum of g of alpha. We can show this by way of contradiction. Suppose that this is L, this is L bar, and this is L tilde. Now, f of alpha plus g of alpha has a supremum which is L, which means that for every epsilon that is greater than 0, there exists alpha tilde, which is in this set S, such that f of alpha tilde plus g of alpha tilde is strictly greater than L minus epsilon. Now, what we do is that we assume, to have contradiction, assume that we don't actually have this inequality. We have the opposite inequality. Assume that L is strictly greater than L bar plus L tilde. If this is the case, then L minus this sum is strictly positive. So what we can do is that we can set epsilon equal to L minus L bar plus L tilde over 2. So we have f of alpha tilde plus g of alpha tilde is greater than L, and then for positive epsilon, we make this choice, L minus L bar plus L tilde over 2. So this is equal to L plus L bar plus L tilde over 2. Now, by assumption, L is greater than the sum. Okay, so this is strictly greater than L bar plus L tilde plus L bar plus L tilde over 2. And so this is L bar plus L tilde. And L bar is the supremum of f of alpha. And L tilde is the supremum of g of alpha. So this is strictly greater than or equal to f of alpha tilde plus g of alpha tilde. Now we have a contradiction because we have a quantity here, f of alpha tilde plus g of alpha tilde, being strictly greater than itself, which is impossible. And so this assumption cannot be true. And indeed, we have the supremum of the sum is less than or equal to the sum of supremum. And a maximum is a special case of the supremum. We have shown that the nuclear norm applied to the sum A plus B is less than or equal to the nuclear norm of A plus the nuclear norm of B. The nuclear norm is indeed subadditive. It obeys a triangle inequality. Now we want to show that the nuclear norm is submultiplicative. Let's go back to our matrix A, which is of size m by n. Now consider B. Now B is of size n by L. The product is of size m by L. The nuclear norm of the product AB is summation J from 1 to the rank of the product AB, which is less than or equal to the minimum of rank A and rank D. And here we have the singular values of AB in non-ascending order. Now our task is to show that this is indeed less than or equal to the nuclear norm of A times the nuclear norm of B. In order to do this, we use the min-max and max-min characterizations of the singular values of a matrix. What is the kth largest singular value of matrix B? One way to characterize this singular value is to solve the following optimization problem. For every subspace in the L-dimensional complex space, the subspace has dimension L minus k plus 1. This k is this k. Over this subspace, what do? Over all vectors in that subspace, vectors with unity L2 norm, we maximize the L2 norm of Bx, of the vector Bx, which is a vector of size n by 1. For each subspace with dimension L minus k plus 1, we obtain the maximum of this quantity, the maximum of this L2 norm. What is sigma k of B? The kth largest singular value of matrix B is the minimum of the maxima. Now let's focus on the optimal subspace in this optimization problem. Let's call this S1. So S1 is a subspace of the L-dimensional complex space. S1 has dimension L minus k plus 1. It is the optimal subspace in this problem, which means that S1 contains the minimum of the maximum. But in the subspace S1 itself, we are solving a maximization problem. So sigma k of B is greater than or equal to the vector L2 norm of Bx for every x that has unity L2 norm and is in this subspace S1. The kth largest singular value of the product AB. We can characterize this singular value by the following optimization problem. For every subspace of the L-dimensional complex space, the subspace has dimension k, which is this k here. What do? Over all vectors in that subspace with unity L2 norm, we minimize the L2 norm of the vector, which is the matrix AB times x. The kth largest singular value of AB is the maximum of the minimum. Suppose that S2 is the optimal subspace. S2 has dimension k, is a subset of the L-dimensional complex space. Now, in this subspace, we solve a minimization problem. So sigma k of AB is less than or equal to the L2 norm of ABX. This is true for every x that has unity L2 norm and is in this subspace S2. What is dimension S1 plus dimension S2? We add this to this, L minus k plus 1 plus k. That's L plus 1, which is strictly greater than L. So S1 and S2 are both subspaces of the L-dimensional complex space. However, the sum of their dimensions is strictly larger than L. This means that the intersection of these two subspaces is non-trivial. It is not just the all zero vector. Now consider vectors in the intersection. If vector x is in the intersection, then it is in S2. And we know that for vectors in S2, we have sigma k of AB is less than or equal to the L2 norm of ABX. So we have this inequality because we are talking about x in the subspace S2. Now, if we consider matrix Y and non-zero vector Y, then by definition, the induced L2 matrix norm of phi, which is its maximum singular value, is the maximum of this ratio, the vector L2 norm of phi y divided by the vector L2 norm of y. So we maximize here over non-zero vectors y. Because this is a maximum, this is greater than or equal to the vector L2 norm of phi y divided by the vector L2 norm of y, which means that the vector L2 norm of phi y is less than or equal to the L2 matrix norm of phi times the L2 vector norm of y. Let's apply this here. So the vector L2 norm of ABX is less than or equal to the induced L2 norm of matrix A times the vector L2 norm of BX. Now the induced L2 norm of matrix A is the maximum singular value of A, sigma 1 of A. What about this vector L2 norm of the vector BX? Note that X is in the intersection. So X is in the subspace S1. And in this subspace, this L2 norm is upper bounded by sigma K of B. So the kth largest singular value of AB is less than or equal to the maximum singular value of A times the kth largest singular value of B. What is the nuclear norm of the product AB? It's a sum K from 1 to the rank of AB of the singular values of AB. Now, we have an upper bound on this singular value. It is less than or equal to sigma 1 of A times sigma K of B. We can take this outside, and so what we have is that the nuclear norm of AB is less than or equal to the maximum singular value of A times summation K from 1 to the rank of AB sigma K of B. The maximum singular value of A is less than or equal to the sum of the positive singular values of A. And this summation is upper bounded by the summation going all the way to rank of B. Recall that the rank of AB is less than or equal to the minimum of rank of A and rank of B. So this is an upper bound. This is the nuclear norm of matrix A, and this is the nuclear norm of matrix B. The nuclear norm is submultiplicative. The nuclear norm of the product AB is less than or equal to the nuclear norm of A times the nuclear norm of B.